Taking the video. So I think there's a couple of things missing on here. So I'll give you a Part B, but Part B is not going to be much. But I figure we'll just review all of these. And I'll leave you this practice test to work from. So we'll review from the book. Any questions? Have you guys worked on any of these practice problems? Starting with I will give you the full reaction like this, but there's some examples here that I can use. So I'll write these out, but so for someone said y'all can't see the answers to these red ones. Can you see the answers to these red ones?
Yeah.
You can? Whoever asked me that. I think you have to go all the way down here, right? Answers to red exercises. Chapter 1, Chapter 2, Chapter 3. So you should be able to find them. If you can't find that, email me again and I'll send you a screenshot of all this. But there's no reason why you shouldn't be able to see those, I don't think. So anybody have trouble seeing these? All right, I don't give you the answers to these because I figure they're there. But if you can't see them, just email me again. Where was I? Exercises. So I'll do 381 and 382 here. So this is a limiting reactant problem. So you got to figure out the limiting reactant and then you can solve it. But I will give you one there. I would say this. Na2. So I'll give you the balanced reaction for these. There is some balancing you have to do in specific places, but in general, I will give you set balanced 2 Na, 2 of those, 2 of those, 2 of those, and the CO3. Okay, so 3.50 grams of sodium carbonate. Five grams of silver nitrate. Grams. So we're going to need, since this mentions grams, we're going to need the grams per mole. So Na, there's 2 of them. CO, there's 3 of them. What is it for sodium?
$22.99.
22. And AgNO3 will be and what is silver?
107.87.
All right, and we're being asked to calculate. I won't ask you about the leftover reactants. Sodium carbonate, silver nitrate. So we're going to need those too. So now, silver nitrate. 2 of those. That one. That one. And sodium. So you guys see what I'm doing over here on the left? You recognize it. All right, I'm going to cheat. Make this quicker. I think that's everything we need. Okay. Limiting reactant and excess reactant. You remember how to do this? What do you do first? You pick one. Either one of the reactants. So I'll just pick Na2CO3, 3.50 grams. Grams per mole for that. Grams. Sodium carbonate is 1 mole. Right. And then 1 mole of this to 2 moles of this. Now the grams per mole for this. You can get all that set up. Let's say need this much silver nitrate. So what we get here, 3.5 times 2 times 169, 873 divided by 105, 8. I got 11.2 grams of Na or Ag. I need that much, but I have anybody else following along? Why do I think that's wrong? 3.5 times 2 times 169, 873 divided by 105. 8. Okay. That's what I got. So if I need this much, but I have this much, what does that tell me?
Limiting.
Yeah, I don't have enough, so this is limiting. And that one's in excess. So now I need to predict amounts of products. So I'm going to use this one as my key to figure out how much products I get. So the question kind of alludes to this being the limiting one, because it's asking about grams of this, but I'm just going to have you find the grams of these, Ag2CO3. So I need 5 grams of that, 169, 73 grams, EGN3, all. And then we'll do silver carbonate first. So 2 moles of AgNO3, 2 moles of that to 1 mole of this, AgCO3, and then the grams per mole for this is 1 mole is 1 mole AgCO3 is 275.745 grams. And then that results in grams. Five times 275.745 divided by 169. Yeah, 3 significant figures. 4.06 grams. So that's how much we predict to get from this reaction, given this many grams of each of these. What else do we call that? What I just calculated.
Theoretical yield?
Theoretical yield. If I did this reaction, and let's say I got 3.95 grams of that, that's the actual. So the actual yield, you don't calculate, you find that in a lab. So you really kind of have to be given that if you have one of those types of problems. I have some theoretical yield and percent yield problems in the practice test. So I'll go ahead and do this, but if let's say that was the actual yield, then you go actual over theoretical, and that gives you your percent yield. So in this case, we would put 3.95 grams over. I suppose I'll calculate it. I get 97.3. So limiting and excess. Like I said, so I'll squeeze that one onto the test. Precipitation reactions. Okay, 4 exercises. This little set that I gave you, so 421 through 424. Let's do 426. CR2, SO43. I should put aqueous here. NH42, CO2. Okay. So you start from there. This probably isn't balanced. In fact, it couldn't be balanced until you have the products. But you're going to take the positive ion with the negative ion. Charge on sulfate. I'll give you that chart again with all the polyatomic ions on it. SO4 is 2 negative. So what's the charge on chromium here? You have to infer that from what you're looking at.
3.
Yep. So CR2 is 3 plus. NH4 is 1 negative. There's 2 of them. CO2 is 2 plus 2 negative. So if we're going to swap these, we're going to have CR with CO2. So plus 3, and this is CO2 is 2 negative. So we again have to have, so you have to balance these as well.
It says
So-
CO3.
Oh, it is CO3. And it's 2 negative. So we did these two. Now we're going to put NH4 together with SO4. SO4 is 2 negative. We can balance this. Again. All right. 2 of those, and there's 2 of those. We need CO3. That's wrong. So CO3 is 2 negative. No, it's not. CO3. Is that right? Yeah. Okay, CO2. Got 3 SO4s. That gives us 6 NH3s, NH4s. So that's going to be 6. 2 of those SO4, 3 of those 6 NH4s, 3 CO3s. Now it's balanced. So for a precipitation reaction, what are we looking for next after this is balanced?
The insoluble compounds.
Right. We have to figure out what we need is one of these to be soluble and one of them to not be soluble. And if we have that, then we can do a precipitation reaction. You can use, I put on here what I think is a better chart to follow from a different textbook for solubilities. This is the one I plan on giving you. Where is it? Notes for test 2. Did I not put it up here? I guess I didn't. Dogs. Yeah, I guess I didn't. I thought I did. Dogs. Oh, it's that I gave you. That's what I thought I gave you. Is that everything? Maybe we better just use the one in the chapter. So it's this. So we're deciding which of these are soluble and which ones are not. NH4. That's probably why I like that other chart. So anything NH4 is soluble, any ammonium is soluble. That one is aqueous. And then the carbonates. So remember in this chart, anything carbonate is insoluble except for these. So is chromium carbonate soluble or insoluble? Based on that. This is anything carbonate is insoluble except for these. Alkali metals are the first column over here. Chromium is not there, so that's telling you the distance. Solid. If both of those were soluble, you would just say no reaction. because you wouldn't really be forming it. Aqueous means these ions are split out in the water. If this was soluble as well, those would be split out in water and you wouldn't get a product. So since that's the precipitate, is that all there was to that question? Should have written the number down. Which one of these did I just do? Oh, I did this one. Okay. The net ionic equation. I always tell you guys to do the complete ionic equation first. There's 2 CRs here. It's 3 plus. And you should put aqueous there. SO4, 3 SO4s, Q minus. There's 6 NH4s, aqueous. 2 times 3 is 6, and then there's 3. Okay, and this is 2 CR plus aqueous. Oh no, because this is solid, we just bring it straight down like that. And then now we have 6. Aqueous plus 3 SO4 SO4. Okay, so what are the spectator ions? Do you remember what spectator ions are?
It's kind of like not.
The spectator ions are the ones that are still ions over here. They don't come back together. So it's the spectator ions that we drop out. It's SO4 and NH. And now here's the net. This is the complete equation. So that's what these are called. So the net ionic is 2 CR aqueous plus 3 aqueous. Kind of a long walk. That's how you solve these. Guys, remember this? You want to do another one of these? Yes? Okay. Maybe I need food. I feel weak. BaNO3. minus. All right, so I'm taking the positive ion and the negative ion, and that's balanced as it is. 2 negative and 2 plus, so that's good. I don't need any more subscripts. And then potassium nitrate. And that's -1 and that's +1, so that's balanced as it is. One of these, I know I need 2 potassiums here, so I'm going to put a 2 here. That makes 2 nitrates, but I have 2 nitrates there, so that's good. 1 Ba and 1 SO4, that's actually balanced now. Right, is that balanced? 1 Ba, 2 NO3, 2 K, 1 SO4, that's balanced. I'll go back to the chart. Just because I know we'll get lost trying to come back. 4.26. So I'm assuming y'all have been using this if you've been practicing. Barium sulfate. There's sulfate. And we're in the part of the chart where these are all soluble. So this is saying all sulfates are soluble except for these. And barium is in the exceptions. So that is not soluble. I think all nitrates are soluble. No exceptions for nitrate. So this is soluble. So we do have a precipitation reaction going on. That's the precipitate. Complete ionic equation would be Ba2 plus aqueous plus 2 NO3s aqueous 2 Ks, 2 potassiums, 1 plus 1 SO4 aqueous. I'm just going to write BaSO4 aqueous 2 NO3 aqueous. So the spectator ions here are the NO3 and the K. So what's left? SO4, and this is the net ionic equation. You guys okay? So I think the examples in the back of the book for those are straightforward. Let's do some redox. Redox 449. But we did 450. do any of these the other day? Do you remember which ones? I'll just pick one. Let's do.
We did the cobalt, iron, zinc, lead, and then the phosphate one.
So let's do, we didn't do aluminum.
We didn't do aluminum, mercury, or iron oxide.
I did the lead. All right,
I think it's iron oxide.
let's do the aluminum one. We have two. I don't think the states matter here. Gas. Solid, okay. What's the oxidation number for this one? It's elemental. 0. This one would be 0. This one's elemental as well, so it's 0. All right, so now we'll look at this. There's no charge on this. It's not a polyatomic ion. You've got 3 negative 1s here for fluorine. Like if I ask you what's the charge on fluorine, you look at the periodic table, you count over 1, you go negative 1. Total of negative 3. So this has to be, actually it's totally predictable because it's aluminum, but this has to be
+3.
plus 3. So 3 plus and 1 minus. Fluorine goes from 0 down to negative 1, so we say it's been, what do you call that?
Oxidized.
If it goes down, it's either been reduced or oxidized.
Reduced.
Which means this one so which one here is the oxidant?
Fluorine.
Yes, fluorine. The thing that's being reduced is the thing that causes oxidation. That's all these statements down here. Undergone oxidation. What else should we do? The iron oxide we haven't done yet. So Fe2O. 3. Two Fe, 3 CO3. All right. What's the oxidation number? 0. It's elemental, so it's 0. None of the other ones are elemental. Okay, O3, there's no charge here. 2, negative 2, negative 2. Total of negative 6. Putting a 0 here because there's not a charge here. So there's an Fe and another Fe. And those have to add up to what? What does that have to be? So you've got 6 positive charges that have to be split into 2. So you're going to have, so it's iron 3 oxide. So That's 0. So here, if if oxygen is -2, carbon has to be that's 0. 2 plus 2. So plus and 2 minus. -2, -2, -2. 3 -2 charges. That's 0. So this has to be +6, and there's only one carbon there, so 6 plus and 2 minus. So first, since the word reduced can literally be interpreted as the charge goes down across the arrow. Iron is 0, okay. So iron goes from +3 down to 0. So that's reduced. That's reduced. And carbon goes from +2 up to +6. So as this reaction goes, which one of these gains electrons?
Iron.
Yes, iron charge went down. That means it gained negative charges. So it's reduced, gained electrons, and that means this one lost electrons. You guys okay with this? You guys study over the weekend? You did? I did nothing over the weekend. I even waited till this morning to try to make a practice test. Redox. These on concentration. That's the solubility chart. Concentration, so 4.61. Probably didn't do the red one, but I'll do the red one. Yeah, I got picky on these. 67A. 73. Did I do this one? 4.73. I probably didn't because it's red. I'll do 4.74. All right, so what we call the dilution formula. Do you remember what it is? It's phonetic, you can kind of remember it. M1V1 equals M2V2. M is molarity, V is volume. And you're always given 3 out of 4 of these, and you're solving for the 4th. The ones are the stock solution. So this is saying how many milliliters of a stock solution. That's the molarity of a stock solution, 6.0. I'm not putting the units here, but it's moles per liter. 110 milliliters. So you need 110 milliliters That's the question. All right. You need 110 milliliters of 0.5 molar. need 110 milliliters. 0.50 molar. 500. So that's 3 significant figures. That's only 2, the way it's written. And you only get 2 here. So our answer is going to be 2 significant figures. So what we're solving for, I know students get confused on this, but this is actually very easy. M1V1 equals M2V2. So I just plug them in, 0.500 V2, M1 is 6.0. My calculator says 9.166666. 2 significant figures is there, so 9.2 milliliters. You would get 9.2 milliliters of the stock solution, and then you would add water up until you got 110 milliliters, water, pure water, to dilute it. Does that make sense? The only other variation here, one of these up here, just based on the definition of molarity. I'll just do 4.61. So now it's telling you to calculate the molarity. If you have 0.175 moles of zinc chloride and 150 milliliters of solution, milliliters. It needs to be in moles per liter, so you're going to have to do this. Since this only involves zinc chloride, I'm not putting the label on here, but all of these could have zinc chloride in the parentheses. What do we get? So we're going to end up here in, that's backwards. No, it wasn't. Number 1 liter. Is that what I had before? Yeah, I lost part of my brain this morning already. 0.175 times 1,000 divided by 150. I think we have to have 2 significant figures here because there's not a decimal there. The calculator says 1.16666. You could write it either way. So that's how you calculate the molarity. So this one would involve the grams per mole, 4.62. Does it say 12.5 grams? Na2 CrO4. CrO4. It's chromate. But we need, since it mentions grams, 22.99 CrO4. 4. And what is chromium? Grams per mole for chromium?
52.
52. I don't have all these memorized. Where's chromium? Oh, yeah, 52.00. But I'm going to cheat, use my little app here. Na2 CR 4. So there's my grams per mole. So this is how you're going to get moles for the moles per liter. CR04. All right. What am I missing? 750 milliliters. Solution. So I'm just putting dash SOL because it's sodium chromate solution CrO4. I do it wrong. Volume needs to be on the bottom. So that's given in the problem. I'm just going to write SOL for solution because I'm running out of room. All right. 1,000 milliliters is 1 liter of the solution. Don't do it. Grams cancel, mole stays there, milliliters cancels to liters, and calculator says that. This leaves us with 2 significant figures. 0.10. You follow that? This. .61C. It's asking you for volume. How many milliliters? This. So moles of HCl. I'm going to leave the labels off. The molarity, the moles per liter, 6.1 moles per liter. That's the same as 6.1 M I could also write this moles over 1 liter. Since I'm being asked for a volume, I need the liters on top. So I'm going to say 1 liter, 6.1 moles, and I've still got to do, it's asking for milliliters, right? Milliliters, so I'll have to go. I'm going to erase that. So I've got moles per liter here. I've just got it inverted. And that should tell me. Divided by 6.1. Calculator says but we've got 2 significant figures, right? 6.1. So we're just keeping that, so you would say 25 milliliters. So if you needed 0.150 moles of HCl, and you had this solution, you deliver 25 milliliters of that solution, you would deliver that many moles. Concentration. Dilution. Another thing I haven't put in that test, practice test, is the heat capacity stuff. So I'll send you a Part B this evening to that practice test. Capacity. Heat capacity 5.53. These. You'll need more examples of these. Five point 5.53 specific heat. So it's 2.44. Joules per gram, and it's got K there, but you can immediately go joules per gram per degree C because it's a delta T. Where are we being asked? How many joules are needed? Okay, so the temperature from 80 grams, temperature 80 grams from 10 temperature 1 is 25, it's temperature 2, yeah, in 3 significant figures. All right, so your delta T, or you could call this initial and final. Sometimes you see TI, TF, but it's always final minus initial. So. 15 degrees C, joules, 1 gram, 1 degree C. And then up here, I'm going to put the delta T. So that'll make this cancel, and then I got to make grams cancel, and then I'll have joules. It's 80 grams. That'll do it. That'll give you joules. Number of joules. Three significant figures. My calculator says 2928. If we're keeping 3, then it's 2930. I could also write 2.93 kilojoules. You okay with that?
I might have just not been paying attention, but how do we go from Kelvin to Celsius there? Is it
Because it's a
tangible?
delta, they're the same. The increments between the lines on the Kelvin scale is the same as the increment between the lines on
Got it, okay.
degree C. So this is 283.15, and this is 789. Can't do that in my head. I'm half brain dead today. $298.5. It's going to equal 15 either way, is my point.
Okay, I get it, okay. Thank you.
What else? Yep, there's another thing. About Hess's law. So these, we did that one. I would have done 5.64, but I'll do 5.63 here. Do y'all remember how to do these? So this is Hess's law, where he used different chemical reactions to find the delta H for one. So we're trying to find the delta H for this one by using these. So the process is like this. P406, there's P406, but it's got P406 on the right. We need it on the left. So I'm going to take this one and flip it around backwards. When I do that, I change the sign. So I'm going to go P406. P4302. And I change the sign, so I'm going to write 1640.1 kilojoules. And I'm going to make it positive now because I swapped it around backwards. I need P410 on the right. This one has P410 on the right, so I'm going to keep it how it is. P4. P4 of 10. And it is 290, 2940.1. All right, we need this to add up to P406. Plus O2. 202. P410. Okay. I think this just works as it is. All right. I've got 302 over here and 502 over here. So 302 will cancel 3 out of 5 here. So I'll have 2 left. Did you understand that? Okay. Get P406. Oh, the P4 cancels as it is. So we're left with O10. So we didn't have to multiply through by anything. So we didn't have to multiply any of these, so we just add this straight up. We need one where we do multiply through. Okay. If I'm following the rules correctly, I've got 1, 2, 3, 4, 5 significant figures, 1, 2, 3, 4, 5. And both of these have 1 after the decimal. So even though my calculator said that at the end, I still need to say 0.0. 800 kilojoules. So this reaction, is that endothermic or exothermic? Is it gained heat or lost heat overall?
So lost.
If it's negative, it's lost heat, so it's exothermic. That's endothermic, the way this is written. That's exothermic. And the overall reaction ends up being exothermic. Let's try this.